We had to use a sledgehammer to get it into the basement, by the way. You will need one to get it out. So let's see. That's supposed to go. There it goes. All right, so my name is Bob Weiss. I'm PW Crack almost everywhere. I'm the owner of a business called Password Crackers Incorporated. I'm also a DEF CON goon. Who goes to DEF CON? Anyone? Anyone? Harris, Amelia?
I wish.
You wish?
I wish.
Never?
No.
All right, so I got to encourage all of you to go to DEF CON. It is, if you can sort of think about the people that you're meeting here, times 15,000. So it's great. You got 5 talks going on all at once. And if you do go, look me up. I'm there all the time because I'm working, so I have to be there. I'm one of the speaker goons. We sort of get the speakers on the stages, off the stages, move them around, make sure everything is happening. We have our own little team. This is our patch. Basically from this year it says, I got you to this stage, I can take you out. I'm going to donate this to the Hackerspace tonight. You guys can maybe get like a $5 contribution for it or something like that. So figure out how you want to get rid of it. But basically I was thinking, first person who gives $5 to the Hackerspace gets the patch. So anyway, these are fairly hot commodity. That's right, they get traded at DEF CON. So you could probably get some other goon to do something for you at DEF CON by trading this patch back in. So where does this go, Amelia? To red. I see cash, so
Greg can hold on to it.
So yeah, okay.
Wow.
It's a rental fee.
Who's the
Treasurer.
Ryan.
I thought you were.
All right, I should probably. All right, fine.
All right, this was the next thing was just something I saw once that I thought sort of summed up kind of what it is to be a hacker. We don't learn to hack; we hack to learn. And a lot of the things that you do, you're just sort of doing it to sort of see what happens and to see what's going to come out of it. It's not something that is like, oh, I want to be a hacker. Teach me how to do it. You don't do it. You don't learn it. You do it, right? And then you learn something coming out of it. That's sort of something that I thought summed up sort of what it is to be a hacker for me. I have a lot of people on my network on LinkedIn, always looking for more. So if you're not already connected with me on LinkedIn, just search for Robert Weiss and PW Crack, and you'll find me. Definitely hook up with me, and let's get connected. And on Twitter, I'm at PW Crack as well. So for today, we're going to do a little leitmotif that'll go on while we're talking about passwords and rainbow tables and stuff. So the talk was called Somewhere Over the Rainbow Tables. And the leitmotif is basically we're going to bring in a little pieces of L. Frank Baum's book, The Wonderful World of Oz. It was a series of books, about 12 or 13 children's books. And back then, children's books was sort of like the grim fairy tales, whatever. They were extremely violent. And his plan was to sort of, just take out some of the sex, take out some of the violence. You still got a lot of eye gouging and death and flying monkeys and people getting eaten by lions and stuff like that. But compared to what came before it, this was a sort of a big step, and it was sort of the first step towards making actual books for children that are what we think of as a children's book. Sort of a light and happy, and Barney the purple dinosaur. Why couldn't he be extinct? So anyway, so we're going to do a little bit of L. Frank Baum's books, and so for today I'm Glinda the Good Witch. And there's some differences between the L. Frank Baum books and the actual movie. So you're all familiar with the Glinda the Good Witch in the movie. But in the books, Glinda the Good Witch is sort of experienced and seasoned and knows that there's not a magic cure for everything. She's sort of the voice of reason in the books. So I'll be Glinda the Good Witch for today. All right, so a little bit of history of rainbow tables. This one, the subtext on here is going to be the Wizards of Oz. Rainbow tables are a refinement of an earlier, simpler algorithm originally created by Martin Hellman. And if you recognize the name Hellman, he is the Hellman in Diffie-Hellman. The Diffie in Diffie-Hellman is a guy named Winfield Diffie, who also spoke at DEF CON this year, his first year attending. So DEF CON 19 was Win Diffie's first DEF CON. I got to meet him, which was cool. So it's originally created by Martin Hellman. The Hellman algorithm was then improved in 1982 by Ronald Rivest. Ronald Rivest is the R in RSA. Rivest, Shamir, and I forgot the A.
Egelman.
Egelman?
Egelman.
Egelman, okay. And mostly what we think of today when we're talking about rainbow tables was Philip Exlin. As far as I can tell, that's the correct pronunciation of his name. I did research it. I'm not sure about it, though. Proposed an improvement in 2003. And it was the Philip Exlin improvement that really got things kicked off in terms of the password cracking community. That's where things really start to come from, sort of 2003. And you'll see his paper is referenced as sort of the Rainbow Tables paper. Prior to that, it's a little bit more theoretical and not as much of an implementation. And he really nails it and figures out how we can do it. And that goes back to 2003. So you're talking about something that's fairly recent, right? This does not go way, way back. And I call them the Wizards of Oz. These guys who really did the big thinking to get it started. Now, to understand rainbow tables, you probably want to know sort of, well, if I wasn't using a rainbow table, what would I be doing? So I call this is sort of the cowardly lion approach, not using a rainbow table. And basically, in various IT systems, rather than storing the password in plain text when you log in and then comparing your password to the password they have on file, what you store is the hash of a password. So rather than sending your password over the wire in clear text in order to authenticate you, we have a piece of software that logs you in, takes your password, hashes it, sends the hash over the wire, and the hashes, when you logged in and created your password, only a hash is stored at the other end. Password hashes can be brute forced and basically try every possible password, hash it, and try every possible hash and try to find the correct one. And those are programs such as Jack the Ripper, Hashcat, Cain Enable, etc. Basically, they're just going to try every possible thing, and that's brute force. And it takes a very long time to do that generally. Another faster way would be to build a possible table of all of these passwords. Just take every possible password, hash them all, save it all one time, and then when you present it with a hash that you need to crack, all you do is look it up in the table. But of course, the table gets very, very large as you have lots of passwords, lots of possible passwords, you're going to get very, very large tables. So that's not very practical, takes up a huge amount of storage space, and would be a big problem. So the conventional alternative is not very exciting. So what is a rainbow table, and how does it optimize those two possible options? This is the standard definition of a rainbow table. A rainbow table is a pre-computed table for reversing cryptographic hash functions, usually for cracking password hashes. Tables are usually used in recovering plaintext password up to a certain length from a specified character set. It's a form of time-memory trade-off using less CPU at the cost of more storage. So if you think of brute forcing as very CPU intensive and creating a big table is very storage intensive, rainbow table is supposed to use a little bit of CPU and a little bit of storage and bring the two together and create something that sort of optimized down the middle. And I forgot to mention, if I say anything that no one gets, please interrupt me. I don't need to give a speech, and it should be very informal, and I don't care about being interrupted. So if anyone has any questions, like that. The train goes by, I'm just going to stop. So you're doing this time memory trade-off, and there are lots of times in computing where you will do time memory trade-offs. Compression is a time memory trade-off. You can compress data and save space, but obviously every time you want to use the data, you have to decompress. So you save a bunch of space at the expense of some CPU time, or you might opt to not save the space depending on what you have and how often you're going to go to that data and which is more valuable. So how do rainbow tables work? So back to L. Frank Blum, Nick Chopper. Does anyone know who Nick Chopper is in The Wizard of Oz? Mm-hmm. Who said yes? Red knows, because I told him last week.
You did.
Yeah. So, Nick Chopper is the original Tin Man. So does anyone, the Tin Man, most people don't know how the Tin Man got to be the Tin Man. So he starts off as a woodsman, and he's chopping down wood, and he falls in, he's a regular sized munchkin, by the way. and he falls in love with another Munchkin girl, and the evil witch doesn't want them to be together. So she enchants the woodsman's axe, and the enchanted axe starts taking off pieces of the woodsman as it goes. And the woodsman realizes that he can sort of put himself back together with the aid of the tinsmith by sort of putting on different limbs. And the axe just keeps taking parts of him off until he's nothing left but tin, and he has no heart and can't love the girl anymore. And it's the only love story in the entire Wizard of Oz book. So it's, if you think about rainbow tables as Nick Chopper, right? It's chop, chop, chop. That's what we want to remember for rainbow tables and how they work. So the problem is if you've got this non-reversible, does everyone know what a hash function is?
Yeah.
Sort of, yes. All right, so it's a non-reversible function. We're going to take the password, convert it to a hash, but we can't go from the hash back to the password. Otherwise, there'd be no point to even looking these things up. So you've got this hash, and you want to create a table, but you want to save the storage space. How do you create a table that's going to, a rainbow table in this case, that's going to allow you to look this up? And this is sort of, for me, you know, I've been using rainbow tables prior to creating the talk. And at one point in time, I was like, you know, I really don't know how they do that. And it was like, how do you get from the hash backwards and be able to look it up if you're not storing all of the possible hashes and you're not just looking them up in the table? So I started researching that, and I figured that's sort of the meat of the presentation, the piece that I wanted to share with everyone. So what you do is you sort of step one, or the easy version, the Nick Chopper version of the rainbow tables, is you define your character set. Say we're going to define it as uppercase, lowercase, and numbers. And we're going to create a rainbow table of up to 7 characters. So the rainbow table could include a password of 1 character, 2, 3, 4, 5, 6, or 7, but not more than that. So we're going to just randomly pick a particular password as long as it's in that set. You could pick AAA at the beginning, or you could pick JKL, whatever. 7 doesn't make any difference. You pick a random password and you hash it. And you take the hash, and you need to create a function called a reduction function, which converts that hash to any other password as long as it's in the character set, as long as it's only letters, numbers, uppercase, lowercase, and less than 7 characters. You create that reduction function, and that reduces it back out, and you get another password. Hash that, take the hash, and take the reduction function, go back, and keep doing that. And what you're going to store in your table, in your rainbow table, is the password that you started with. And you're going to do this hash reduction function password, hash reduction function password loop, or in rainbow tables talk a chain. You're going to do that X amount of times, let's say 10,000, until at the very end you're going to end up with hash, right? And you've entirely picked these at random, though your reduction function should always come back and pick another random password somewhere in the chain. So you're going to start off with a password, and you're going to end up with 10,000 operations later, a hash. And that is going to be your rainbow table. You're going to take those 2 elements, save them, and then pick another random password. And keep doing that, do it again, go back and forth, create all these functions, and then store that chain, again, those 2 items, and then do it again X amount of times. The number of times that you do it and how many times you, how many operations in each, I'm going to get to you in 1 second, is going to define sort of how accurate your rainbow table is, yes?
So is this like a differencing engine then?
Kind of.
I mean, is that what it does? Is it just, does it decide what the difference is between your first password and first hash and then the second password and the second hash?
It's more going to be, it's going to be closer to a lookup table than a difference engine, if I understand what you're talking about.
And your reduction functions, like these 10,000, they're all different. Or they are all the same.
That's the next slide.
Okay.
For right now, just assume that there's a reduction function which takes a hash and just makes another password out of it. Okay? We're not trying to get back to the original password, we're just trying to get back so that we can start all over again and come up with a hash. And because the hash is almost random, if you use that same reduction function, you're going to get, you started off with a random password, you're going to do this all kinds of times and end up with 10,000 times down the road, you're going to end up with a hash, and you're going to store those two things together. So you're only storing two values, even though I did 10,000 operations with 3 different numbers. The only thing I'm going to store is that first password that I chose, and then the hash at the very end of doing it 10,000 times. Then I'm going to pick another random password. So I might have 50,000 passwords and 50,000 hashes in my rainbow table. But 50,000 is a fairly small number. That's going to be a fairly, fit on a floppy disk, right? So that's going to be a fairly small number, even though I've done a lot of operations to get to that. And I've pre-computed that, okay? So that is what your rainbow table looks like. That's all the data that gets stored. Yes, Pierre?
Why do you do it 10,000 times instead of doing it until you get a loop?
The reduction function within one chain shouldn't loop back on itself. Should not. We're going to get to that in the next slide as well. But you're going to pick it a particular number of times based upon how accurate you need your table to be and how many hashes you need to. For instance, if you need a rainbow table that's going to be able to recover a password from within the character set, a defined character set, with 99.9% accuracy, you're going to have to run longer chains and more of them. If you just need to basically be 77% accurate and probably be able to recover most of the hashes, then you don't have to run as many chains, and you can optimize that. You can end up with a smaller rainbow table. But obviously this will affect the size of the rainbow table and the amount of time it took to pre-compute it to build the rainbow table the first time. All right? So if you're storing that, how do you get to, here's a hash, I need to find the password, or I need to find the original plaintext, how do you get that? Okay? This was the part I thought was really cool. You can't look up the hash. There's only 10,000 hashes in the rainbow table. Your hash is not one of those, probably. The odds of it being one of those is very small. So what you do is you take your hash, you run your reduction function, you get a random password from your hash. You take that password, hash it, and check that hash to see if it's in the list. If it isn't, you run the reduction function, get a password, come back out, hash it again, check the hash, is it in the list? If you do this 10,000 times, one of the 10,000 passwords that you generate going forward from the hash that you gave should be in the list, right? If you generated enough hashes on the outside for your table to be reasonably effective, then you should get a hit at some point in time going forward 10,000 times. Again, if we're using that as the example chain length. What you then do is now you have found a hash which is in the chain that ends with this hash. You then go back to your table, find the password that started that chain, take that password, hash it, run the reduction function, run it forward until right before you're going to get to your hash that matches, you go backwards one step and that was your password. So that was the really cool part that I thought, oh, I get it, that's how they do that, that's pretty cool. And that's what Weiss and Hellman come up with. That's sort of their innovation. So now, one more step. How do rainbow tables work part 2? And I call this slide flying monkeys, right? This is when monkeys are going to come flying out of my butt. Now it gets just a little bit more complicated, all right? Instead of using a single reduction function, this was what Philip Exlin invented, right? This is the next step that makes this all somewhat practical. Instead of using one reduction function, for each of my 10,000 steps in the chain, I'm going to use a slightly different reduction function. Previously, if you only had one reduction function and you use that same function over and over again, as Pierre somewhat alluded to, you have the possibility of what's called a collision. And once you hit a collision, once you reduce back to a particular password in 2 different chains, the chains are from that point forward going to be the same chain and they're going to end up with the same hash. And now you've got the same hash resolving backwards to 2 different original passwords. That's a collision. It messes with the accuracy of the table and basically makes those 2 chains not worthwhile. So So if you use that same reduction function, you end up with too many collisions generally in a very big file. But if you were to define your table so that you've got 10,000 steps in each chain, and each of the reduction functions in that chain are different, now in order to have a collision, you'd have to hit the same password with the same hash. It would have the same hash in the same place in the chain. So it's hitting the same password doesn't necessarily kill the chain unless they were both at step 669. And if they both were hit the same password with reduction function 669, then from that point forward there'd be a collision, but the probability of that happening is significantly reduced. So what Philip Exlin says is, as we're doing that reduction function and coming backwards and going forward, modify your reduction function at each step in the chain slightly so that you minimize the collisions and you minimize the possibility of the chains colliding. I say, so it gets a little bit more complex. Now in order to reverse the hash, you, this is even hard for me to say. It's probably even more hard for you guys to follow. But here's, you're presented a hash. You take reduction function, if we're going with 10,000, 9,999, reduce it back, get a password. Reduce it back, get a password, hash it. Does that hash match? No. So now we can't just keep going backwards because we have to run it in reverse order. Now we've got to go back, take reduction function 9,998 from the hash, get a password, hash it, and then use 9,999, go forwards. So each time you can't just sort of run one after the other because you're not using the same reduction function. You've got to step backwards 2 steps, 1 step, run it forwards, see if the hash matches, then throw all that out, go backwards 2 steps, run the whole thing forward, see if it matches, and then start all over again because the functions that you're going to be using each time are completely different. So it gets a little bit more complicated, a little bit more CPU intensive, but it actually makes the whole thing work a lot better. So I call that flying monkeys because it starts to get really complicated. So what are the current practical capabilities of rainbow tables? What can I do with this stuff if I had it? Okay. You guys know what LANman is, Windows passwords, up through XP. I believe Windows 7 still supports LANman passwords. And if you take it out of the box and you create a password on your system that is less than 15 characters in length, and it's up to 14, up to and including 14, Windows will store a LANman hash. It's incredibly weak, and all of those can be cracked 100% with a very small rainbow table almost instantly. NTLM is, if you type in your Windows password and you type in a password of 15 characters, the system no longer works with LANman, so it'll create an NTLM hash. NTLM hash is also stored in the other systems, but if you have a shorter password, we would not crack the NTLM hash if we've got both because it's harder. So we can crack with the rainbow table an NTLM hash up to about 9 to 10 characters in length, letters, numbers, uppercase, lowercase, letters, and numbers. If it's got special characters, then you might have to notch that down to about 7. We can also crack SHA-1 hashes up through 8, and again, depending on the character set, etc. Amelia?
You're saying that we can crack them. What's the storage and CPU requirements?
Right, so different tables for different algorithms take up more space. Some of this, CPU is basically not a factor. This is not a very CPU intensive operation. Some of the rainbow tables, the largest one that I've seen is 500 gig. So on a I talked to Rob Fuller. He's going to get me. He said yes, I can have it. Yes. I have to send him an external drive. Okay. So it's going to cost me like $150.
I will help with that.
Yeah, I'm just going to ship it to him and say, put it on here. And as soon as I get it back, then I'll create a torrent of it and whatever. So a little inside thing that we've been working on. So I'm in the process of getting this NTLM 500 gig database. Again, it's the largest one that I know about. but most of them can run in sort of the 100 meg range, or 1 gig, something like that. So they're definitely downloadable, definitely storable on what most of us would have as sort of a home computer system these days. In order to use it, I'm going to get into the software, definitely something you don't need an elaborate system for. If you're doing a whole heck of a lot of them, or you've got tens of thousands of hashes, then maybe you need some acceleration. So MD5 SHA-1, if I say that the character set of possible passwords is only numbers, then we can take MD5 up to like 12 characters, and it's numbers only. So somewhere in that range, you're going to be able to recover a password from a hash within seconds using a rainbow table, and you can just go download what you need in a relatively short period of time. Right, so reduced character sets, if you reduce the character set, the length can go out a little bit longer. And people are building new tables and using distributed systems and GPU acceleration every day. So it would not, I would expect that you're always seeing new tables coming out, new tables being released. So this is only getting bigger, right? The number does not go down, it only goes up. You can use rainbow tables for anything though, so it's not only hashes for SHA-1, MD5, NTLM, LM. Office 2003 has keys, and LCOMsoft has a product called Thunder Tables which uses that, and OffCrack also sells a commercial product. You could build a rainbow table of Unix crypt passwords, MySQL hashes, Cisco PIX hashes. Any system that has a hashing algorithm, you can build a table for it. What you're doing is you're saying, look, I'm going to spend some time up front to pre-compute this. I'm going to run it. I might be running this machine for 3 months or 6 months to build this table. But once I have it, I can post the thing on the internet, someone can download it in an hour and start cracking hashes within seconds. So that's basically the plan, and people are building these things. And people keep coming out with new algorithms and new systems all the time, and someone will build a rainbow table for it. As I say, it's an arms race. Using rainbow tables, you can download your own rainbow tables. Typically, they'll have the extension .rt, and then use a variety of software to test your hash list. Rainbow Crack is probably the preeminent one, but John the Ripper, Cain and Abel also support using rainbow tables in the .rt format. Tables can vary in size from a couple meg to a couple hundred gig, high Quincy. And again, Rainbow Crack, OffCrack, Cain and Abel all use RT files. So how do you defeat rainbow tables? How do you protect against someone who's going to build these things? So this is the Wicked Witch of the West, always trying to stop Dorothy from reaching Oz. Rainbow tables, by definition, require pre-computing and can be defeated by adding unique salts to the password. So how would I salt a password as a for instance? So I'm running a computer system, and I'm going to store a hash, and I'm going to authenticate you by a password that you provide. So, so when we create your logon, you're going to provide a password, and I'm going to add to that a salt value. It might be a 4-character or 8-character piece of data, and I'm going to take your password, stick the salt on the end of it, hash that. I'm going to store the hash, but I also need to store on my system the salt. Now, when you come in to authenticate, you're going to say, hi, I'm Bob Weiss. I want to authenticate to the system. The system says, here's your salt. You type in your password, stick the salt at the end of it, hash that, send the hash back, and if the hash matches, then we're good, right? You're authenticated and you're allowed into the system. So the salt is pretty much a public part of the authentication system. It's not meant to be kept secret. Salts can travel in plain text over the wires. They can be captured by hackers, right? But adding that means that now I would need to build a rainbow table for every possible salt value. So I don't have to build one table with all the salts in it. I have to build that many tables. Go ahead, Quincy.
So is it sufficient to just use the username as the salt?
That would be a significant improvement over not using a salt, right? So the problem that I would have with using the username as a salt is the real password, the one that I want to get, Oz, trying to reach Oz, is I want admin, right?
Right.
Well, admin is the salt. So here's the table I'm going to build. F all the other usernames. I'm just building admin, right? And there are rainbow tables pre-built with admin as the salt for that situation. So now, if you defeat it, if you took admin off the list and made the admin password Quincy, that would probably fix it. But this is not the best plan.
Okay.
But it would be an improvement over doing nothing. Okay.
With what he was saying, WPA2,
Right.
every router actually uses a
Right.
different.
I'm going to get to that one.
one.
Right. I mean, it's
Salt.
SSID as the salt. Right.
Yeah.
So salting makes the pre-computing a problem, right? Once you get to a salt, basically it makes it so that, again, I can't really pre-compute an entire rainbow table for every salt as long as there's enough complexity in the salt. The problem with crypt is it's a 2-byte salt, and that's probably not complex enough. That reduces the number of rainbow tables that I would build to how many? 32? Yeah.
6 squared.
A 2-byte salt.
2 bytes, yeah,
So
8
you need
squared.
65,536 tables.
Okay, right, so 65,000 tables. So
Except
that's,
it's ASCII only though.
the crypt salt is ASCII only?
It's ASCII only, so it's going to be
Alright.
about 38. So about 38 squared. So it's a large number.
Right, it's a large number, it's not an
It's not
undoable
impossible.
number. Right. And one of the ways we talked about doing that was just building the salt right into the list of passwords, so that if basically we would just do all of them with all possible salts and run that as the password list. So for an 8-character password, we would need to actually run 10 characters. It would be a big table, and it would be hard to do, but it would be really cool, and I can definitely guarantee you talk at DEF CON about the project if you can finish it. Because you'll be in the biggest room at DEF CON because everyone's going to want a copy of that table, right? You don't release the table until you get to DEF CON. So that's doable, but basically, again, salting would do it. WordPress has a fixed salt, right? So there are certain versions of WordPress, and all the passwords are salted with this one salt. That is not how this is supposed to work, right? So there have been rainbow tables that have been pre-built with the WordPress salt, and I think there's 2 different WordPress salts right now, based upon if you're in this group of versions or this group of versions. Yeah, go ahead.
Does WordPress even use SSL or any other type of encryption by default? I don't think it does. I think it stores plain text by default. I think you have to have like...
No, I think it stores salted hashes.
Does it
by default? Yeah, I think.
For users.
For users, right.
But not the actual transfer of data back and forth.
Right.
That's just being
Well, again, this is assuming that you're running the WordPress software, not WordPress.com, but that you've taken the software, you're running it yourself. Basically, that's almost as bad as just using plain MD5, or whatever. It's not. They haven't salted it. It's just like got a fixed constant in it. Go ahead, Pierre.
And that's what I call the salt that has lost its savor.
Okay.
For what it's
Go ahead, Red.
For what it's worth, the WordPress side is going to be less secure if you're running it over SSL than more. Because
Really?
You're not going to see my attacks if I'm attacking you through SSL.
Yeah, that's a good point. Well, that's
Right.
if you really wanted to get down to it, I mean, you could always open up the PHP and change, randomize the salt yourself.
Right. Well, it is. Yeah, it's open source. You can fix their vulnerability. Obviously, The vast majority of sites don't do that, which is why WordPress gets continuously owned, and usually in large blocks of quantities when it happens. So anyway, so this is again how you would defeat rainbow tables is you make that algorithm fundamentally more complex, typically by salting it. Don't write your own algorithm, right? Typically, if you're not a professional cryptographer, you will probably do damage to it by coming up with what we call roll your own in cryptanalysis. You say, oh, he rolled his own stuff. I can run a couple of very simple tests on the hashes to see if you created a really secure algorithm or not a secure algorithm. And if I know that, wow, they did something custom, they rolled their own, and it fails some of the NSA tests, you know, it's like, but then you're just asking to be owned, right? And say, generally, if you're not a professional cryptographer, you have no business trying to improve on the algorithms.
What if you took a product like WordPress and you obfuscate the code with like Zen or something along those lines?
Right, yeah, so obfuscation or security by obscurity, again, is typically what we're talking about. It's not an improvement, not where you want to go. And as I say, you do better to stick with sort of the well-known algorithms and implement them correctly. And they're all out there, they're all, you know, open source, so that's a very easy thing to do. Usually people think, oh, I'm going to get really creative, you know, I'm going to XOR it, and then I'm going to XOR it again. Wait a second.
With 2 different bytes.
Right. If you XOR something and you XOR it again, you got the plain text. You know, like, that doesn't exactly work. So anyway, so let's move on. So WPA. So if has anyone researched WPA cracking, WPA2? So you know RenderMan? Does that ring any bells? Okay. So RenderMan, always at DEF CON. I'm plugged into DEF CON. So what they did is they said, you know, let's take the so WPA encryption includes as the salt the SSID of the wireless access point. So it has its own algorithm. So it's a WPA algorithm, and part of that algorithm is we're going to take the password that you create or the key, and we're going to hash it together with the SSID as the salt. However, problem: most people don't change their SSIDs. So there's a lot of SSIDs out there called Belkin 54G, Linksys, wireless access point, right? Admin, etc., etc. People don't come up with what? Public. Right, public access, open wireless access point. Yeah. So, so Google has been driving around, you know, recording all these access points and you know where they are, etc. And there's a huge database of them, right? And names of wireless access points are very publicly available, even if it's encrypted and you can't access it. The names are available, so you can make a list of them and sort it and say, let's say, well, what if I took the 1,000 most frequently used access point names or SSIDs, right? Well, so then we're going to take, well, what if I took, you know, let's say, so does anyone know what RockU is?
Yes.
Red knows what RockU is? All right, so RockU, this is, how many years ago is RockU? Oh, I think more than 2. I think that goes way back, right? So RockU's a big website, lots of people sharing music and chatting with their friends and got the social content going and all the rest of that. And they get owned and all of their hashes get released. And a bunch of password crackers then take that hash list of RockU, which again has millions of users in it, and start cracking the passwords, okay? The end result is they get almost all of them, right, using mostly rainbow tables, and you now have a username and a password combination. But the importance of RockU is it was the first really big site to get owned and exposed in this way. And what it gave is it gave everyone a look at how humans create passwords. You know, it's like, well, what if I had a database of 1 million actual live passwords from people? You know, it's like, what kind of passwords would I be seeing? You know, I might see password a lot, you know, God, sexy, you know, whatever, Van Halen, you know, Captain Kirk, you know, whatever. So this was sort of a social, you know, fun website It wasn't a business website. It didn't have a password rule that you have to change your password every month or something like that. But it was the first big website to come out. So like, well, what if I took the million most frequently used passwords? Let's say I take the RockU database. I take the ones that are top million, and I hash those together with the top 1,000 most frequently found SSIDs, and I build a table out of that. That's what RenderMan did, and the end result is a torrent of about 33 gig. The first one they did is, I think they took the top 1,000 passwords and 1,000 SSIDs, and they figured, oh, we can do a better job of that. And then there's a piece of software called CowPatty, C-O-W-P-A, obviously, and they put this whole thing together. So if you were, you need to find a password on a WPA access point, you've got a hash, or a value that you need to look up. No biggie, if the SSID is in their table times 1,000,000 possible passwords, there's a good chance it might be in there. On his website, he calls this a rainbow table. Okay, this is not a rainbow table. This is a table, right? It's 33 gig for a reason. It's every possible password combined with every possible SSID in a big table. You just look it up, right? So not a rainbow table. He calls it a rainbow table. You cannot make a rainbow table out of this, right? Because a rainbow table is going to be every possible password within a character set, combination, and a particular size requirement. This is a lookup table, right? We can't make a regression function or a reduction function that's going to go back and end up on one of the 1,000,000 most likely passwords and combined with one of 1,000 SSIDs. So it's not a rainbow table. At some point, somebody may create a WPA rainbow table doing all of the possible passwords combined with all of the possible salts, but that's not what is out there right now. That's another cool hacking project waiting to be a DEF CON talk. And in my experience, by the way, if it's possible to be a DEF CON talk, it usually will be very soon, right? There's probably someone out there who's working on it right now, and they've already figured that out. Because talks tend to build on each other, right? Somebody does one thing, and then a year or two later, someone else says, "Oh, we're going to take that to the next level." So it's like, yeah, someone says, "Oh, we could drive couches around the street," and next time they're timing them down the quarter mile, right? So it's like these things tend to build on each other and come out. So anyway, online services. This is the scarecrow in the story. So most people think of the scarecrow, he lacks a brain, he needs to go to Oz to get his brain back. What you learn in the L. Frank Baum books is the scarecrow is actually very young. He's only 2 days old. And it's not that he lacks a brain, but it's just that he has the mentality of a 2-year-old child. He's a newborn, right? And later on in the story, he's eventually going to be the smartest person in Oz. So he's not there yet, but it's not that he lacks a brain, it's that he's going to be the smartest person in Oz. And these are the online services. There's a lot of places you can go online where you just take your hash that you're trying to look up and find the password to. You have to know what algorithm created it. And you just go to Free Rainbow Tables, Online Hashcrack, AskCracking.com, MD5Online.net. There's a whole bunch of them. There's probably 20 different sites. Those are the biggest ones up front. And you put in your hash, paste it in, and it tells you the password. You're like, why would I download all this software and get all these rainbow tables if I could just go to the website and do it? That's an excellent question. Also, the websites are accumulating everyone else's rainbow tables, right? That's how they do this in the first place. So generally, they're ahead in the arms race right now. So you're using kind of the best resources, and they're the easiest to use. These are definitely the smartest guys in Oz, right? I mean, eventually they're going to get there, and they're going to have more capabilities than you have, and you can't keep up with that. The last one I added is a Python script, find my hash.py. You run the script, put in your hash, and it goes to all 20 sites at one time and checks them all out, right? I mean,
It's a scraper, that's great.
exactly, yeah.
That's
So
awesome.
it's you know, again, this is where it's going to go. You know, this is becoming easier and easier, and sort of that's a picture of the future. That's why again he plays the scarecrow. So creating rainbow tables. Well, so why would you want to, if you could go online, why would you want to create your own rainbow table? Well, most of the online services only support the big ones. So Landman, NTLM, SHA-1, MD5 are typically well supported. But the software that we use to create rainbow tables, which is called RT, you need RTGen and RT-sort, the combination will create a rainbow table. And then there's also a Windows GUI WinRTGen, which is actually what that picture is. That software supports a whole range of algorithms that are not as broadly supported. So if you happen to have a MySQL SHA-1, or you have a SHA-2 512 password hash and you need to crack that, you're probably not going to find one of the online services. You may, in fact, have trouble downloading a rainbow table from out there in the world because there's not that much stuff out there that's been created yet. So you may have to build your own rainbow table. And if you have a project, these are the tools that are out there right now. You can do this. You basically just, type in, the hash algorithm, minimum length, maximum length, index you don't need to worry about, the chain length, and the chain count. That's the number of calculations in each chain, the number of chains that I'm going to run, and click on benchmark, and it'll tell you how long it's going to take to build the table, and the probability of success of finding a hash in the table you're about to build, and how much space it's going to take up. I mean, I just use it to test how big the files are going to be. It's like I don't necessarily need to run it. You just want to know. It's like, oh, here's what I'm looking at. If I did this calculation, I spent this much time on it. What would that look like? So it's a great manage your project with that. So it's really simple to build your own rainbow tables. And again, that's typically you do that if you're working with a little bit more obscure algorithm, and you probably have a little bit more of a long-term approach. You're probably not going to do this to hack into a wireless access point, right? I mean, you can get free Wi-Fi at Starbucks. You're like, why would I spend 6 months building a rainbow table, and going through all this machinations in order to, get some trivial payback on the back end? But if you have a project, it's like say, hey, we need to test the security of, this particular database or this website or something like that, and they're using this. This would be a great, sort of proof of concept tool project you can run and say, hey, your website's not secure. We were able to put these resources in, run it for 3 months, and now we own all your passwords. The last one is you should be aware. There's also now GPU accelerated rainbow tables generator at cryptohaze.com. I just added that recently. So their tables, they do not generate .rt tables, which is somewhat important. And so their software works with their rainbow tables that get generated, but if you really need to build it fast and you've got a lot of GPUs in a machine, that's another option to go with. But it's going to be, it's an open source tool, but it's a closed system, right? It's not going to be compatible with the other tools, which normally RT is. Okay, I think the next part is on the next slide, I hope. Yeah, RT naming convention. So all of the rainbow tables that you're typically going to find are typically extension .rt. And the Rainbow Crack software and most of the other software needs the file to be named in a very specific way. And the file name tells the software, and the file name is going to look like this. And it needs to look like that. That's how the software works. So typically, people don't come up with they don't call it real big rainbow table file.rt. They have to leave the name the same. So when you go to a torrent, you're going to see .rt, and it's going to have all this stuff, which tells you exactly what's in it. the number of chains, the length of the chain, number of chains, the algorithm, the character set, minimum passwords 1, maximum passwords 7. Right? So that tells you what that rainbow table does and what it was designed for. And they typically don't get renamed because Rainbow Crack or our crack needs that. And then there's that sort of the extension there of what each of those naming conventions are. So you can look at a rainbow table and just by its name tell what it was designed to do and how it works and what it's going to do. If you want to know how accurate a rainbow table is, get WinRTGen, that little Windows thing, type in all of those numbers, hit benchmark, and it'll tell you, oh, this is a rainbow table that's 95% accurate. You never get to 100%, by the way. Well, I guess with the Landman, you could probably get to 100%. But theoretically, it shouldn't be. I know it says 100% on it. It shouldn't be, because unless they've tested maybe they have tested every possible password, you wouldn't know that you've gotten every possible hash in this way. But anyway, so you can test to see. So a lot of times you'll see, someone has put out a rainbow table, and they've got this whole thing there, and it takes up 3 gig. And then another one puts out, it's the same algorithm, same character set, same number of characters, and theirs is 4 gig. Well, why do I want the 300 meg one or the 4 gig one? Most people would say, well, the 4 gig one's got to be better, right? Because it's bigger, right? Well, that's not the way rainbow tables work, right? It'll be faster to recover any particular hash. The bigger one will be faster, and it may be more accurate, but the accuracy might be the difference between 99.5% and 99.7%. So you may be downloading a much bigger file to get a very small amount of accuracy, but for instance, if I've got 10,000 hashes that I need to get, having a table that can reply back and generate each hash back to me 4 seconds faster could be an issue. If you've only got 1 hash to recover, you don't really care, right? Then in fact, you're going to be downloading a really big table, spending extra time doing that, and it's going to take you longer than it would have taken you to recover your 1 hash with the smaller table. So, so you can look at the naming conventions and you can decide for yourself which rainbow table you want to download and what you're getting before you spend the time doing it. Most hackers that I know who are doing rainbow tables, who are doing hash cracking, just collect these files. They download every rainbow table they can get. They've got piles of external drives. They're storing as much data as they can, and they pretty much don't know what they have. Right? There's not sort of this mental calculation. They might have 4 different versions of this thing, and they just, oh, there's a new rainbow table out. I'm gonna, it's like, my collection must be good because it's the biggest, right? This is not about that, right? This is not what this is for. You want to have the right tool that you need and go get the other ones. I would respect someone who's got some more of these exotic algorithms because they're a lot harder to find. So that's so the naming convention tells you exactly what you're getting, and you can use it to determine the success of the table if they don't tell you that in the torrent or whatever. And the Emerald City. So these are a bunch of sites where you can download rainbow tables. Shmoo is really good. It's almost always up, and it has the most popular big rainbow tables there. Hack5 has 2 different tables listed in their forums, only one of which is active. FreeRainbowTables.com has a ton of tables. But FreeRainbowTables.com, they are, their stuff is compressed down. They store it in .rti format. Then they give you a tool that can convert from .rti back to .rt. So you should be aware of that. It's not that big of a hurdle to get over, but they're a little bit different. They not only make their files, Free Rainbow Tables not only makes their files available for FTP download directly, but there's also links to torrents. WPA was created by Offensive Security. It's also at the Shmoo website if you want to get the WPA table. Again, it's not a rainbow table. Cisco Pix and MySQL torrents exist. They are not active, not being seeded, and I don't have them. I would really love to get those torrents or get those files. Free Rainbow Tables up here has a link to the GAR mirror, which the link is over here, and they have even more tables listed there, but mostly, and they're divided down by algorithm and size, so those are sort of the most, if you Google Rainbow Tables and download, you're going to get these sites most often. That's where most of the stuff is. If you go for the torrents, I have now downloaded all of those and some others, and I'm now seeding them. So it's all of the files that I have are at 100%. I'm seeding them back out. So one of your peers is going to be me. And that tells you, it's like, well, if you're going to go get a 30 gig file, at least if I'm one of the peers, you're going to get it eventually, right? Might take a while, but I do have 100% on them. My server just stays on feeding that stuff out, so it's always going to be out there. And then what Red and I were talking about in the middle there is there was a really big Rainbow Table of the NTLM hashes, which is Windows. A lot of people are really interested in that, and so there's already some out there, but this one was fundamentally larger than a buddy of mine. It's a buddy of mine, and if anyone knows, sort of follows the Hackers Who's Who, it's Mubix. Does anyone know who Mubix is, or remember that name, Red? All right, Harris. So his name's Rob Fuller. So he had this really big file, and he offered to give it to me at one of the Nova Hackers meetings, and so I told him yes. So I just shot him an email yesterday. He emailed me back today. I was like, yes, he has it. He'll give it to me at the meeting. And I'm like, I don't know how we're going to transfer that in a meeting, Rob. I mean, it's 500 gig. If you bring a laptop in it and it's on a laptop, and I bring you an external drive, how long is 500 gig going to transfer over USB 2?
8 hours, 8 to 10
8 hours, 10 hours, yeah. So I was like, that ain't gonna happen, So I said, why don't I just ship you an external drive? You can put it on, let it run, put it on, ship it, and I'll give him a reply envelope to send it back. So that's our plan. He said, sure. And once I get that, I'll put it on the server. I'll create a torrent, and I can share that torrent as well. Once I get it, it'll be seeded. I'll put a link out there to it as well. So, so this is again sort of, you want to be selective about what you have. You don't need to create this huge collection to say, I have the biggest set of Rainbow Tables or whatever. Download what you need and be thoughtful about what you're downloading and what your tools are. If you're doing thousands of hashes for a project, yeah, you probably want the biggest, fastest one you can get, and yeah, you should have terabytes. But if you're occasionally looking up one hash, or you want to sort of test the capabilities, you probably don't need that big. And you can test these things with relatively short passwords in the real world. So that's it. Any questions?
What did I miss in the beginning?
Let me start from the beginning. Let me go back over the whole frickin' thing.